and welcome to day 5 of our Unit 14 Notes for Statistics in Algebra 2R. Today's focus is going to be on margin of error on the middle 95% interval. Now, when you guys think of margin of error, you likely already know something about it. Like if we say a political contestant is likely to get 70% of the vote with a margin of error of 2%, that's give or take 2%. So you could be confident you're within 68 to 72% for that candidate. So it's the same idea for what we're doing in class. So I'm going to show you where margin of error comes in with all the statistical analysis that we've been doing. Below is a simulation of flipping a coin 4,000 times. So there are 40 times per trial. 100 trials. So what that means is that your sample size is 40. So you flip the coin 40 times. You recorded the proportion of heads and then you plotted a point. So n equals 40 is your sample size. There are 100 p-hats in this distribution. So every one of these dots is representing the proportion of heads in one sample of 40 flips. And then you repeated that 100 total times. So if you take a look at our distribution here, I have my lowest p-hat right there and my highest one over there. Now the x-axis, to be honest, isn't great, so I'm just going to estimate what these would be. I'll say my smallest p-hat or proportion there was 0.32, and the largest is 0.72. Now, would you have expected these possible results before you started your simulation? So if you were to guess, flip the coin 40 times and you're going to say 32% of the time you'll get heads or 72% of the time you'll get heads. Is that something you'd likely say? Probably not. You'd probably say something closer to 50%. So, you know, anywhere like, 55% of the time or 62% of the time or, 48% of the time. Something closer to that mean. 0.32 and 0.72 seem pretty extreme. So no, I wouldn't say that I would have expected those. Is it possible that they happen? Sure. They just don't happen that often. So those are called extreme dots on either end of our distribution, and they are not expected results. So we consider them unusual because they happen rarely. In order to come up with my middle 95% interval, I'm going to disregard a total of 5% of my data because those are my most extreme results. They don't happen often, so let's throw them out because they're not going to help me estimate like a good interval, a good proportion of when we're going to get heads. So since this distribution has 100 dots, how many dots should we disregard? Well, there's 100 dots. And I throw out 5% because those don't happen that often, that would leave me with 5 total dots. Now, when you throw out 5 total dots, you want to try to evenly do it from either side of the distribution. Now, obviously, 5 is an odd number, so it's either 2 and 3 or 3 and 2 dots from either side. So we're just throwing out our unusual results. So I can just see that I can nicely throw out these 2. And I'm going to throw out these 3. And that leaves me with my middle 95%. So everything I just highlighted in blue there is representing your middle 95%, which is the stuff that's likely to happen. If there were 200 dots in this distribution, and I wanted to figure out how many dots to throw out, 5% of 200 is 10. So I would have thrown out 10 dots, so 5 on either side. So again, in other words, by us throwing out the 5% of the data on either end here, we're leaving the middle 95%. So my lowest p-hat now that I would consider a reasonable guess for my next flip is like 0.38, so I'll say at 38%. And the highest one I'll say is at like 64, I'll guess. 64 is 66. Let's actually say 66. Sure, 66. I'm just guessing there. So again, if I were to reasonably take one more sample of n equals 40, so flip my coin 40 times, I could reasonably expect to get between 38 and 66% of heads. And that just helps me estimate my next sample. So let's say I increase my sample size. So now we're looking at n equals 60, or excuse me, 160. So that means you flipped a coin 160 times, you recorded the number of heads, you figured out the proportion, and you plotted a point. Okay, so this is just the interval of heads per sample of 160 tosses. If I were to reasonably take one more sample between 160 coin flips, I could reasonably expect to get somewhere between this percent and this percent. So again, the extreme results don't happen often, so I wouldn't include them in my interval for guessing my next coin flip. So I can see these two right here are pretty extreme, so I'm going to throw those out. And I actually use pen. So these two I'm going to throw out, and these three I can throw out. So 2 and 3. Again, I could have done 3 and 2. I just kind of go by what the distribution looks like. I'm just estimating here. By throwing out those extreme dots, again, I threw out 5 of them because there was 100. I'm throwing out 5%. It looks like I'm landing between 42 and 58. So that means if I were to get another p-hat in this distribution, I can reasonably guess that that p-hat would be somewhere between 0.42 and 0.58. And that's my middle 95% of data. So on the next page, it says, as sample size gets larger, our spread of sample results gets closer or tighter to the center or mean of our distribution of sample proportions, or means if we were looking at means. In other words, our margin of error gets smaller. Okay, so what that means is if you look at our previous page, after we threw out the 5%, we were saying our p-hat, our next p-hat could reasonably be between 0.42 and 0.58. We also said when we had a sample size of 40 that we could reasonably be between 38 and 66. So with that increase of sample size from here to here, so again, I increased sample size, you'll notice that that window or that interval got tighter together. These numbers aren't as far apart as these numbers were. Now, like we said, if this is your normal distribution from your data, this is like where your center is, right? So this is your middle 95. Your margin of error is how much you could reasonably expect above and below the mean would be to capture your middle 95. So from here to here, this is your margin of error, and from here to here, this is your margin of error. So, like we said, as our sample size increased, our margin of error would then decrease because that interval is getting tighter for our middle 95%. Now, in order to calculate our margin of error, because it's, two margin of errors fitting in that middle 95, we're going to use this little formula right here in the box. Margin of error equals highest reasonable expectation minus the lowest reasonable expectation divided by 2. Or I'll write it like this. Margin of error equals high minus low divided by 2. So Kathy was surveying students about average studying time for the AP exams and found an interval for the plausible population mean for a given sample size of 40 students to be between 5.3 and 16.5. So that's how many hours they're studying. She then increased her sample size to 160 students, and her interval then changed to 8.4 to 12.2. So you'll notice that interval got tighter, right? These numbers aren't as far apart as these numbers were. Calculate and compare the margin of error for both intervals. All right, so you got n equals 40 and n equals 160. So starting with n equals 40, we found that interval to be between 5.3 and 16.5 for our middle 95% of data. Margin of error is high minus low divided by 2. So if I go ahead and compute that, that would end up giving me 5.6. So what that's saying, everybody, is in a normal distribution, if this is your mean in the middle, your margin of error, so your wiggle room, is 5.6 above or below that mean. And that would capture your middle 95%. Okay, I'm going to do the same thing with 160. That interval was 8.5 and 12.2. Margin of error is high minus low divided by 2, which would be 1.9. So again, in a normal distribution, if this is your mean, now they're saying your middle 95% has a margin of error of 1.9, which is your wiggle room, which is now less, still capturing the middle 95%. So your margin of error decreased. So now I'm going to go back to my data from the previous page where I determine the plausible intervals for sample sizes of 40 and 160 and calculate the margin of error for each of those. Okay, so on the previous page for n equals 40, so if I scroll back up, my plausible interval for n equals 40 was between 38 and 66. So I'm going to scroll back down. So I'll do 0.38, 0.66 in a proportion. And then for n equals 160, again, previous page, here's the 160 tosses. I said between 0.42 and 0.58. All right, if you want to freeze the screen right now or pause it and compute the margin of error yourself, this would be a good time. Otherwise, I'm just going to go ahead and do it. All right, so high minus low divided by 2 for each of those. I got 0.14 and 0.08. So in each of these cases, I went from 5.6 to 1.9. I went from 0.14 to 0.08. As our sample size increased in both of these cases, we noticed that our margin of error decreased. Maybe I should do decreases. So as sample size increases, margin of error decreases. Now, you know from what we've talked about previously that standard deviation decreases as well. So how are standard deviation and margin of error related? Well, that's what comes in on the next page. So what you all are looking at is a standard normal distribution because that's how a lot of our data has ended up looking. In fact, just about all of it's end up looking that way. Okay, so we have seen that the shape of our distributions of sample proportions and means generated through simulations have been roughly symmetric with a single Maunder peak. We can conclude that even without actually conducting a simulation, we would expect the distribution to follow the properties of a normal distribution. So that's this bell curve right here. Now, below is a standard normal distribution curve, and that's because the mean is 0, which is the middle here, and your standard deviation is 1. Okay? What is the area under the curve between -1 and 1? So that's between here and here. So if you want to find the area under the curve, this is a recall from Unit 13. I would use normal CDF. My low bound is -1, my high bound is 1, mean is 0, standard deviation is 1, and I go to my calculator. So remember, this is at second vars option 2. Low bound's -1, upper bound is 1, 0, 1. And then I'll hit paste. And you'll notice I get 0.682. So to the nearest percent, 68%. So we're finding that 68% of our data lies within one standard deviation of the mean. Let's do the same thing for between -2 and 2. Okay, so pull up my calculator again. Second vars, option 2, -2, 2. Paste, and I get 0.954. Which means 95%. So I'm finding that between -2 and 2, or within 2 standard deviations, we're getting about 95% of their data. That means that's your middle 95%. Now, we just said on the previous page that this amount that you swing above and below the mean is called your margin of error, which helps you figure out your middle 95%. So looking at the x-axis here, I'm noticing that margin of error is equal to 2 standard deviations, which makes up my middle 95 when I swing the margin of error either way. So based on the results above, margin of error is just 2 times the standard deviation. All right, so coming on down, given a normally distributed population of IQ scores with a mean of 100 and a standard deviation of 15, between what 2 scores would you expect to find the middle 95% of the data? Well, first of all, what is the margin of error? This is just 2 times the standard deviation, and they told me the standard deviation is 15, so that would be 30. So in your normal distribution, your mean would be at the middle, so that's 100. And they're saying your middle 95% would be plus your margin of error minus your margin of error. Now, if we just said the margin of error is 30, that means this value right here would be 130. This value down here would be 70. So that means I can reasonably expect that my middle 95 for data would be between a 70 and a 130. So that means if you were to pick another person, you could be reasonably confident that your next person would have an IQ between 70 and 130. And you can be reasonably confident that if you were to find the true average of everybody's IQ score, it would be somewhere between a 70 and a 130. All right, question 2. Given a normally distributed population of SAT math scores, we can reasonably expect that 95% of the scores will be between a 510 and 590. So rather than finding the interval here, they're actually telling you the interval. Your low bound is at 510 and your high bound is at 590. So what's the margin of error? Which, keep in mind, margin of error is here to here and here to here in my distribution if this is my middle 95%. Now, just like I said on the previous page, margin of error is high minus low divided by 2. So this would be 590 minus 510 divided by 2, which is 80 divided by 2, which is 40. If margin of error is equal to 2 times the standard deviation, and I know the margin of error is 40, that means the standard deviation would have to be 20. So using my knowledge of what margin of error is, that means the mean, if I add the margin of error to go to the right, must be 550, which would then make sense to get a 590 for the other side of this. So my mean would be 550. All right, so moving on to the next page. In order to calculate the middle 95% interval for either categorical or quantitative data, it's all about calculating your low bound and high bound based on your margin of error. So you're going to take whatever your sample is, whether it's a p hat or an x bar, and you're going to add or subtract the margin of error. And again, margin of error is just 2 times the standard deviation. Now, something else to note is that in life, we're not going to take samples over and over again. We're going to take one sample, and we'll use the proportion or mean from that one sample to create our middle 95%. We will feel reasonably confident that our middle 95% will contain the true proportion or mean of successes in our population. So we can be pretty confident that our true population mean or proportion lies in that interval. So it's all about making inferences about the population. Okay, so for example 1, a random sample of 36 juniors revealed that 12 of them plan on attending a district-wide junior trip to Marineland in Ontario. So keep in mind, that's a p hat right there. They took a sample of 36 juniors and found 12 of them said yes, they're going to go, which is the same as a decimal of 0.333 for 3 decimals. In order to best estimate the true proportion of all juniors attending the trip, you run a simulation based on a sample size of 36, assuming the probability of junior attending the trip is 0.333. So it's making a simulation based on our sample. You run the simulator 250 times. The results are shown below. So this is like me pulling up that Rossman Chance website, putting a mean of 0.333 in because that was the p hat that I got. And then I did a sample size of 36, so n equals 36, and then it said 250 samples, so 250 times. So that means in this distribution, there are 250 p hats for that. Using the results of the simulation, calculate the middle 95% interval that we can expect to contain the true proportion of all juniors in the district who we can expect to go to Marineland, and round to the nearest hundredth. All right, so when it says using the results of the simulation, this is actually super easy. They're telling you the mean and standard deviation, so forget throwing out dots. That would only give me an estimate. Now I have data, I have numbers. Whenever we're figuring out the middle 95%, which is always on the Regents exam, by the way, I'm just going to do the mean plus or minus 2 times the standard deviation, which is the same thing as the margin of error. So the mean from my simulator is 0.335. The standard deviation is 0.087. And then I just go to my calculator. So if I pull this up, I'm going to plug in 0.335 minus 2 times 0.087. And then I just got to do the same thing again, but put a plus in there to figure out the upper bound. And I get 0.509. So to the nearest hundredth, 0.16 to 0.51. So this interval, like what does it even mean? It means the true proportion of all juniors in the district. So if you were to actually ask every single junior, you can be reasonably confident that the proportion of juniors going on the trip is somewhere between 16% and 51%. So the true proportion of all juniors attending the trip is between 0.61 and 0.51. So again, this is everything that's likely to happen. This is your middle 95. So if 30% of the juniors ended up going on the trip, that wouldn't be shocking to you. That's in your middle 95%. 40% of the juniors go. Sure, that's plausible. But do you think 70 juniors are going to go? 70 would be outside of the interval, right? Anything outside that interval is unlikely to happen. Could it happen? It could. It's just highly unlikely for it to happen because it's falling outside of your middle 95% that you computed using your simulator based on your sample. So based on our findings, would you be comfortable placing a $20 bet that at least 60% of juniors will go on the Canada trip? Why or why not? Well, again, 60% would be somewhere outside of the interval. It's possible it could happen, but it's not very likely. So I wouldn't bet on it. So I'm going to say no. 0.6 is outside the interval of reasonable guesses so it's unlikely to happen. All right, we just got one more question to go. So this was a question of sample proportions. So we were estimating the true proportion of all juniors. Now we're going to practice sample means. So a random sample of 78 bags of potato chips was analyzed and found to have a sample mean weight of 9.1 ounces. We ran a simulation and found the mean to be 9.1 with a standard deviation of 0.005. Find the plausible interval containing the middle 95% of sample mean weights. All right, so it's mean plus or minus 2 times the standard deviation. I know the mean from my simulator was 9.1, so it happened to match my p-hat, or excuse me, my x-bar. My standard deviation from the simulator is 0.005. Okay, so we would just add or subtract that in our calculator. So take a moment, figure that out. So you should end up with 9.09 and 9.11. So again, that's your middle 95%. Anything in that interval is expected, okay? Including 9.09 or 9.11, totally expected. So based on the results, do you think any customers will complain that they are not getting a full bag of chips if the chips are labeled as containing 9 ounces? Justify your response. So take out the fact that people just like to complain. I like to ask the question, well, should they complain? Well, if the advertisement is saying 9 ounces, you're actually more likely to get more than that. So they really shouldn't be complaining because you're on average getting more than what the bag is advertising. So I'm going to write they shouldn't. Despite the fact people like to complain. It's likely they're, oops, I messed up there, getting more than 9 ounces because it's unlikely to get less than 9.09 because that was the low bound of my middle 95% based on my sampling. And that is coming up with the middle 95 and interpreting it. And it's all based on the mean plus or minus 2 times whatever our standard deviation is, which is our margin of error. Now we're going to practice this more in the next lesson as well, because I can just ask a bunch of different scenarios and you got to know how to interpret that middle 95 and how to make conclusions based on it. So this lesson idea will continue into our day 6 notes.